Hi, my name is Julia Silge, and I'm a data scientist and software engineer at Posit PBC. And today in this screencast, we are going to use the Tidy Tuesday dataset, actually from last week, that is all about the songs of Taylor Swift. I know you probably haven't been hearing enough about Taylor Swift in your life and world, but I think you need more. Clearly you need more. The timing is so good because this past weekend I went to see the Taylor Swift concert film. It was a beautiful experience, so much fun. And one thing that I thought about as I went to see this movie was that the nature of Taylor Swift's albums have changed so much over the course of her career. From her later albums are kind of concept-y and very themed. And I wondered, can we learn about that? Can we find evidence for that from the lyrical content of her work? So we are going to use the lyrics, we're going to train a topic model, and then we're going to see how the topics in the topic model are related to album.
Alrighty, time for some Taylor Swift analysis. I'm pretty excited about this. Okay, so I installed the Taylor package that includes this data here for last week's Tidy Tuesday. And you can see here that we have the rows are the songs here. So we have the track name, and then each of these is an album. The lyrics are in here, and that's what I really want to focus on in this analysis is the lyrics. So let us get those out. So notice that if I just print it out like this, oh no, that you can't see it there. But notice that these lyrics here are little nested tibbles. So it has all the lines of the songs are inside kind of like nested. So we'll need to unnest those a little bit. So let's say Taylor album songs, and let's see here. Let's unnest the lyrics like this, and then now we have a lot more rows. Now we have one row per line of the song. Let me just show you what this looks like here. So if we go over here, so this is all track number. Let's go down somewhere. So here is the Archer. And if we go over here, we have one row per line of lyrics like this. So we've reshaped the data a little bit. And now let's use tidy text like this to unnest, in a sense, again, we're going to say unnest tokens. And we're just going to use, let's call the new column word, and the new is called lyric. These are also labeled with like chorus, outro, and whatnot, which would be pretty interesting to look at as well. But let's just do this. So now we're going to have a really long data frame like this, and let us call that Tidy Taylor. Whoops, I cannot type. Tidy Taylor, like this. So now we have one row per word, where word is this this unit of analysis that we are interested in doing. So now we can do things like count up the most common words. So like we could just count words. So I've noticed this when I look at song lyrics before. So in what you might call more regular text, things like the and are clearly the most common. But when you get lyrics, you get things like you, I, and me that are even higher, which I think is interesting. It really points to the differences in language, even in something like stop words. If we wanted to get rid of the stop words, We can do that like this. If we wanted to count up the most important words that are not stop words, the most common words that are most stop word, not stop words, we have things like love, never. These words are, no and time. These are just, very common English words that are not in the stop word list. We also could do something like, count the words by track, which is what we will do here in a little bit. So now we can see the word that is used the most in one song that is not a stop word is the word red in the song Red. Shake here in the word shake it off. In the song Shake It Off is used a lot. So this is us getting this text into a analysis ready format. So now what we want to do is we want to train a topic model. So a topic model is an unsupervised model for text where you say, hey, I believe there are latent topics in this corpus, this collection of documents. And a topic model works in that it says each document is a mixture of topics and each topic is a mixture of words. And it's a pretty effective way to learn something about text in an unsupervised modeling framework. So let's count track name word like this. So the tracks, the songs are going to be the documents here. And then we can use cast sparse. So cast, what we say row, column, value. So we're making a document term matrix. So we say row is the documents. Columns are the words, and here the value is n that we'll get. It's like this n that we have here. Notice that I did not remove stop words. It turns out there is some research out there that removing stop words you typically don't want to do because how the stop words are used can be important in the topics. So it's better practice not to remove those from this. I do notice this is a lot. So my document term matrix, this is the rows, this is the columns, super wide right now. Let's dial that back a little bit because this is going to take a long time and we might not get the best results. So let's keep words that are used at least more than 3 times per song, that are used at least 3 times in a song. Let's throw away the like 1 or 2 or 3 words that are used like 3 times in a song. So okay, this looks better. It's still wide, but it's not as wide as it was. Okay, so this means here we have 194 songs, 194 songs, and this document term matrix has 867 columns, and so that is the words that we're going to have in our model. So I am going to load STM, the STM package for structural topic model, as it's called. This is my favorite implementation of a topic model. And then, so I'm going to make a topic model. So I will call STM. So the first thing we need is the documents, the input here. So I put in my document term matrix. And then, for a topic model, the most important hyperparameter, if you will, is K here. So K is the desired number of topics. There's different, so you can think of this like K and K-means. It's a hyperparameter that we need to decide. There are some algorithms for trying to decide what K should be. There's some sort of rules of thumb here. The most important user input is the number of topics. This is this K here. No right answer. So there's kind of some guidelines here. So if you have something very short, try 3 to 10. If you have something that's a few hundred to a few thousand, 5 to 50, and so on and so forth here. So we have 194 documents. And this is Taylor Swift, so I think we should use 13. I think we should use 13 topics here. So it is done. It is fitted. So this is it's not an enormous data set, so it's done now. And we can see the result, like kind of like a printout here. So notice that the highest probability words are these words like you, I, the, we. And that's because we did not take out the stop words. We did not take them out. Like I mentioned before, this is evidence points to this being the better choice, to keeping those stop words in. It does mean that the highest probability words are very similar from topic to topic, but we have other ways of choosing important words, like FREX, which is high. Is a different metric that is high frequency and high exclusivity, high lift. There's these different ways, these different ranked lists. So like if we look at the first topic, the highest FREX and lift words are things like hair, prayer, rare, red, stairs. This looks like the Red album, especially All Too Well, I think. Looks here. And if we scroll down, we kind of see these different things, Cornelia Street and Trouble and woods and cars and so on and so forth. So we have done it. We have trained a topic model. This summary that we do here is a great way to kind of print something out. This comes from SCM, but we also have the ability to tidy this model. So let's talk about how we can do that. So if we do tidy topic model like this is the beta matrix. This gives us the beta probabilities, which are the topic word probabilities. That's equivalent to this and this. And so let's call this the boring one. The highest probability words are these very common, not so interesting words. We can go in here and we can get out those different ones. Like, for example, we can look at lift here. And so now here are the highest lift words, and it's in order of topic. So here again, we have these rare, hair, rare, prayer, like those are like the all too well words. So this topic one, the highest lift words are look to be from the Red album mostly. So we can go through, there's lots we can do here. I'm kind of interested in how these topics vary over the albums. So we're going to do one more. Instead of the lift, we're going to get gamma. And when we do this, we also need to pass in the document names because it's not kept inside of it here. So that, if we go back here, these are the rows, these are the columns. So it's the rows that we want. So we want row names of that thing, like so. And so let's call this, let's call this lyrics gamma, like this. Maybe let's make this nicer. Okay, so now we're getting out the gamma matrix, and this probability here is the document topic probability. So this one was topic word probability. This one is document topic probability. So I think we'll be able to do something interesting here to be able to connect this back to album name. So we will have this, and then let's left join it with that original data set. We only need album name and track name. It's called document here. So let's say document equals track name, like that. Great. So now we have document topic probability album name. And now we can make a plot. Let's do this. It's more in the middle. Okay, so gamma on the x-axis, topic on the y-axis. Let's say fill equals topic, so we can see this. And then we are going to say geom box plot like this. So, like so. We need to make topic a factor. Topic, because right now it's represented as a number, but really it's a topic like this. So let's say we don't need this. So this is all of them together. You can see topic 3 is the highest probability one. If we go back up here and kind of look at it, topic 3, these words, the highest lift words are like places, trouble, things like that. So 3 is the highest prevalence overall, but we want to look at it by album name, like this. All right. That's looking good. Let's make these so they are in the right order. So I'll say mutate here, and let's say album name, and I'm going to use from forcats the function fact in order, which just it sets the factor in order that you see them in the data set, which in this case is a chronological order. So that will work so that these are all in the right order. All right, nice. Let's make this a little bigger so we can see it a little better. There we go. Okay. Okay. This is pretty interesting, actually. Okay, so from the early albums, lots of topic 2 and 3. Remember we had said that topic 1 looked like it was, all too well in the Red album in general, and it is here. Here, it looks like Red and Midnights have the most for topic 1. And 1989 and Reputation look like they have their own kind of topics that are used in them more than anything else, which is interesting. And then Folklore and Evermore have this topic 13, a little bit in Midnights as well. So it looks like, and we don't see that much at all in these early albums. So remember, this is about the lyrical, like the text content of these songs. So we see that Folklore and Evermore have they have a lot in common when it comes to lyrical content. Reputation and 1980 look fairly unique-ish, but these early albums are like a lot of 2 and 3, and they have like these first 3 albums look like they have a lot in common in terms of the topics that we learned. So great, that's super interesting. So what we just did was we looked at these visually, like I looked at, we just looked at this plot and we looked at it visually. We have other tools that we can use with these kinds of models. So this was let's call this this thing that we did right here. Let's call this a visual exploration of the topics. And what we saw, there was real, right? But we might want to understand from a model-based perspective, how are these things related together? So to do that, we can use estimate effect from the STM package. So first you put a formula where you want to say which topics do you want to estimate an effect for. So let's do it for all of them. Album name like that. We pass in the topic model, and then we need to pass in something that has the album names. So let's go to, I think we can go to Taylor album songs. Whoops. And we want only the track name and the album name. And then we need to make sure these are in the right order. So if we go to our sparse data set, so for example, if we do, so the row names give us the names of the songs in the order that we have them in this document term matrix. So we need to make sure it's in this order. So this is a This is alphabetical here. So we can just do arrange here, arrange track name. And now this will be in the right order. Let's double check that. Yes, okay, so we now have in the correct order what album name we have. So we're gonna say, what we're saying here is, I would like to estimate the effect for these topics from this predictor, this thing that I want to know if there is an effect with it, using this model-based approach. So I can say effects, yes. Oh man. There, like this. I'm setting a seed because this is using draws, like simulations here. It's doing 25. You can bump this up or down, depending on what your approach is. So that worked great. Ooh, lots of stuff printing out there. I think there's actually a summary method to print out something a little bit better. Yes. So this probably looks familiar to you, right? Like familiar, it looks like the output of an LM model, right? So what we have here is for topic 8, what is the estimate of how album is related to topic 8? Notice the p-values here are all really big. So for many of these topics, we don't see evidence that there's a statistical relationship between album and this topic. That is not true for topic 13. Topic 13, we see the little stars, our friends' little stars, for Evermore and Folklore. And then also it looks like Reputation as well for topic 11. So we did a summary here to print out this whole thing and look at it, but we can also use tidy for this. So we can tidy the effects, much like you might tidy an LM model. You can tidy the output of estimate effect here. And so this gives you a data frame with all these things in it, and we can specifically find the things that that we have p-value wise, like evidence of there being a relationship, just using normal old dflyer kind of stuff. So we can say, let's get rid of all the intercepts because that is not what we're interested in. Like this. So now there's just the different albums, and let us, we can say p-value, we could say less than 0.01, and we get those 3, and actually those are all less than 0.05 as well. So this is the, these are the effects, that we have evidence for. So topic 11 is more prominent from Reputation. Topic 13 is more prominent for Evermore and Folklore. So let's look at that. So if I go back to the topic model and I look at that, let's look at that lift metric again. I can say, hey, what if I only want the topics that are from topic 13? So these are the highest lift words from the topic that we have evidence that it comes more from Evermore and Folklore. So we see Betty, we see party, we see houses, these are definitely words that are used in Evermore and Folklore, but are not used in Taylor Swift's other albums.
All right, we did it. We went on a journey through the eras of Taylor Swift's work. We learned how to train a topic model using the text content here, and then link those topics to other information that we have about these documents, which in our case were the songs. We then used models to understand the topics and how the topics may have may be related to other things about those documents. In that case, we looked at album again, and we saw that we we saw statistical evidence that the albums like Folklore and Evermore were similar to each other and came from one topic, and Reputation came from another topic. We did not see evidence for some of those other things that I maybe said out loud when I was looking at it visually, and that's how these things work. You know, like there may be things that we can observe in data that are true. There are things that we see there, but we don't necessarily have statistical evidence that they are related or important. So I hope this was helpful, and I'll see you next time.